everyone. I am Dr. S. Shashi Devi, Associate Professor of Physics, working in Vardhaman College of Engineering.
So in this video lecture, we are going to discuss about the application of Schrodinger wave equation. In the last video, we have discussed about the Schrodinger wave equation, one-dimensional and three-dimensional potential equation. So let us discuss about how Schrodinger wave equation can be verified. So because Schrodinger set up a wave equation for the matter waves, but how that particular equation will be verified. So for that, I am going to take an application here, that is particle in one-dimensional potential box. How a particle is going to vary in potential box. So for mathematical simplification, here we are going to consider the one-dimensional box. Now let me take, this is a one potential box wherein an particle is moving here, a particle is freely moving, particle is inside this particular potential box of infinite height. So wherein here we can see the height of the box is infinite and this particle is freely moving. And let us discuss about what are its eigenvalues and energy values and wave function of this particular particle which is freely moving in one-dimensional potential box. And for mathematical simplification, let us consider the potential inside the box as 0. That is, a constant potential is applied on the particle, a constant potential is applied on the particle. And for mathematical simplification, this constant potential let us consider as 0. That is, inside the box the potential is V of x is equals to 0. As well, we also consider that this box is of very hard and the particles are not at all penetrating out of this particular box. The particle is freely moving inside this particular box and of length x is equals to 0 to x is equals to L. And let us also consider outside the box the potential as infinity of infinite height. So these are all the considerations what we are going to take, and our aim is to calculate what are its eigenvalues and energy values of a particle which is freely moving inside the potential box. For that, let us consider the one-dimensional Schrodinger's wave equation. So we have already discussed the one-dimensional potential box in the last video. So let us take the same expression, that is dou square psi by dou x square plus 2m by h bar square into E minus V psi is equals to 0. This is the Schrodinger's one-dimensional wave equation. Make it as an equation number 1. Now let us apply the first boundary condition, equation 1. First boundary conditions on equation 1. What are the first boundary conditions? As for this particular potential box of one-dimensional, so here the first boundary conditions are V of x is equals to 0 inside the box and V of x is equals to infinity outside the box. These are the first boundary conditions, and the limitations are 0 less than x less than L and 0 L less than x less than. These are the boundary conditions. The first boundary conditions are V of x is equals to 0 inside the box, that is 0 less than x less than L, that is inside the box, and V of x is equals to infinity outside the box, that is L less than x less than 0. These are the first boundary conditions. Let us make this as an equation number 2. Now here we are not interested outside the box, so let us consider only inside the box. So for that reason, I am considering the first condition, that is V of x is equals to 0. So let us substitute V of x is equals to 0 in equation 1, that is Schrodinger wave equation. So it comes out to be dou square psi by dou x square plus 2m by h bar square into E psi is equals to 0, because here V becomes 0. So V is 0, so therefore it comes out to be equation 1 is going to be modified as dou square psi by dou x square plus 2me by h bar square into psi is equals to 0. Make it as an equation number 2. But what is 2me by h bar square? According to quantum mechanically, The value of 2me by h bar square is k square. 2me by h bar square is nothing but it's k square. How? By using lambda is equals to h by p and k is equals to 2 pi by lambda. Kinetic energy is equals to, that is 2me by h bar square is equals to k square. What is k square here? K is a wave vector. K is a wave vector which is given by the value k is equals to 2 pi by lambda. But quantum mechanically it is shown that by using lambda is equals to h by p and E is equals to p square by 2m, it comes out to be k is equals to k square is equals to 2me by h bar square. It can be shown that k square is equals to 2me by h bar square. Let us substitute the same in equation 2. I have already substituted, that is k square is equals to 2me by h bar square. So with that it comes out to be dou square psi by dou x square plus k square psi is equals to 0. It comes out to be dou square psi by dou x square plus k square psi is equals to 0. Make this as an equation number 3 and make this as an equation number 4. Dou square psi by dou x square plus k square psi is equals to 0. This equation is a general equation. Okay, so this equation is a general equation and general wave equation, and the solution for the above equations can be given as psi of x is equals to a sin kx plus b cos kx. The solution for the above equation, above wave equation is given by psi of x is equals to a sin kx plus b cos kx. Make it as an equation number 5. Now to solve the above equation 5, where in equation 5 a, b and k are constants. In above equation 5 a, b and k are the constants. Now here after calculating these three values, we can give the solution for the Schrodinger wave equation and we can find out the particle motion in one-dimensional potential box. And to calculate these constants, let us apply the second boundary conditions. What are the second boundary conditions? The second boundary conditions are at psi of x is equals to 0 at x is equals to 0 and psi of x is equals to 0 at x is equals to L. That is at both the points, at both the boundaries, at x is equals to 0 and at x is equals to L, at both the points the wave function of the particles is 0. Even at this particular point also psi of x is equals to 0 and even at this boundary point also psi of x is equals to 0. That is at both the boundary points psi of the wave function is 0. So let us substitute the same boundary conditions here. That is psi of x is equals to 0 at x is equals to 0 and psi of x is equals to 0 at x is equals to L. So let us apply the second boundary conditions in equation 5 to find out the constants a, b and k values. So let us apply the first boundary condition. Let us apply the first boundary condition. That is psi of x is equals to 0 at x is equals to 0. So that is after this it comes out to be equation 5 is going to be modified as psi of x is equals to 0, 0 is equals to sin k 0, sin 0 is 0. So therefore it comes out to be a is equals to, this is 0 plus b, sin cos 0 is 1. So because 0 is x is equals to 0 at psi of x is equals to 0. So with after substituting psi of x is equals to 0, 0 is equals to sin 0 is 0, that is 0 plus b cos 0 is 1. So it comes out to be 0 is equals to 0 plus b. So it comes out to be b is equals to 0. We have calculated one constant here. So let us make this equation as 6. Now we need to calculate two more constants here. So for that let us apply the second boundary condition. second boundary condition. So where the second boundary condition is psi of x is equals to 0 at x is equals to L. Here it is L. Psi of x is equals to 0 at x is equals to L. So after substituting this particular value, equation 5 is going to be modified as equation 5, that is psi of x is equals to 0 at x is equals to 0, that is a sin KL plus b is equals to, already we have calculated b is equals to 0. So let us apply here b as 0. That is 0 is equals to a sin KL plus 0. So this comes out to be a sin KL is equals to 0. So make it as an equation number 7. But this equation 7, in this equation, both a and k are constants. Both a and k are constants. Both are unknown constant. We don't know the value of a and k. And to satisfy this equation 7, either k or a must be equal to 0. Either k or a must be equal to 0. Okay, but here as a is an unknown constant, I can't make a as equals to 0. That is, a can never be equal to 0. So because it is an unknown constant and we didn't find out the value, I never make it as a 0. So the only thing that I can make a 0 is the sin KL value. That is, sin KL must be equals to 0. Sin KL must be equal to 0, because we know the sin 0 is a 0 value. So I can make this sin KL as equals to 0. That is, or else I can also write down it as KL is equals to n pi. KL is equals to n pi, or else k is equals to n pi by L, or else k is equals to n pi by L. So we have calculated one more constant. So in this here we have calculated two constants. One I have got it as b is equals to 0, one is b is equals to 0, and the one more constant k is equals to n pi by L. But we didn't calculated the value of a till now. A is a unknown constant. So it means after applying the two boundary conditions, but still if you are unable to calculate the one more unknown constant, so then Schrodinger said that we can apply the normalization condition to calculate the unknown constant. So that normalization, by using that normalization condition, let us see how we are going to calculate the value of a. Now the equation 5 is psi of x is equals to a sin kx plus b cos kx. So here we have calculated the value of b and the value of k. So let us substitute both the values here. So after substitution, psi of x comes out to be psi of x is equals to a sin n pi by L into x, because b value is 0 already and kx value k is equals to n pi by L we have already calculated. So it comes out to be psi of x is equals to a sin n pi by L into x. So make it as an equation number 9. Now Schrodinger suggested, even after applying the two boundary condition, but still if you are unable to calculate the unknown constant, he suggested to consider the normalization condition. What is the normalization condition? So normalization condition is integration minus infinity to plus infinity, that is mod of psi of x whole square into dx is equals to 1. But here the psi of x in a particle in one dimensional box is calculated to be, but here our limits are 0 to L. Therefore 0 to L mod a square into sin square n pi x by L into dx is equals to 1. Take the a square out, integration 0 to L sin square n pi by L into dx is equals to 1. But we know that sine square theta is equals to 1 minus cos 2 theta by 2. By using this expression, we are going to solve the above integral value. So that is, it comes out to be a square integration 0 to L, that is 1 by 2 into 1 minus cos 2n pi x by L into dx is equals to 1. So let me take 1 by 2 out, that is a square by 2 integration 0 to L and 1 minus cos 2n pi x by L into dx is equals to 1. This integration, it comes out to be x minus sine 2n pi x by L into, so it comes out to be 0 to L is equals to 1. So after substituting the limits, it comes out to be a square by 2 is equals to 1 minus 0 into, this is 0 minus 0. After substituting the limits, it comes out to be a square by 2 into L is equals to 1, or else a is equals to 2 by L under root. So this is the value of the unknown constant a. Now let us substitute the same in equation. So wave equation, so it comes out to be psi of x is equals to, a value is under root 2 by L into sine n pi by L into x. So this is the wave function. That is, by using the Schrodinger wave equation, here we are able to find out the solution for the wave function. That is, wave function is given by under root 2 by L into sine n pi by L into x value. Now, what are the eigenvalues and energy values? That is, by using both wave function equations, that is wave vector equation, k is equals to n pi by L and k square is equals to 2me by h bar square. By considering both these equations, we have already calculated both these expressions. So let us equate both the equations. So with this, it comes out to be, with both these equations, comes out to be n square h square by 8 ml square. So the energy expression is going to be calculated as E is equals to n square h square by 8 ml square, where n can take values 0, 1, 2, 3 and so on. So with the substitution of these energy values, E naught is 0, this is known as 0 point energy, and E1 is given by h square by 8 ml square, h square by 8 ml square. Now let us calculate the value of E1. So where h is the Planck's constant, which is given by 6.64 into 10 power minus 34. Now let us calculate the h value, where n is taken as 0, 1, 2, 3, and if I am going to substitute n is equals to 0, E naught is equals to 0, it comes out to be, it is known as the 0 point energy, and if n is equals to 1, and for n is equals to 1, E1 is equals to h square by 8 ml square, and it comes out to be, where h is the value Planck's constant, 6.624 into 10 power minus 34. Substitute this value here, and 8 m is the mass of the electron. So and it comes out to be 9.1 into 10 power minus 31 whole square, and L, let us consider the value of L, that is the dimensions of the potential well, as 1 angstrom. So if I consider this as an 1 angstrom, this value comes out to be 34 eV. So this is in joules after converting. So this value is comes out to be 34 eV. And for n is equals to 2, E2 is equals to 4 E1, that is 4 H square by 8 ml square, and n is equals to 3 is E3 is equals to 9 E1, and for n is equals to 4. So this comes out to be E4 is equals to 16 E1 and so on. And here after calculating E2 value, it comes out to be 152 EV and E3 is 342 EV and so on. So this shows that the energy of an particle which is moving in a one dimensional potential box is quantized. That is, as classical mechanics tells us that the energy is released continuously, but quantum mechanics says that the energy is not continuous but rather the energy is quantized. That is, the energy of an particle is released some quantas of energy. That is, in the first quanta of energy, so it is going to be 34 eV, 34 eV electron volts energy is released, and in the second E2 it is released as 152 eV, and in E3 it is released as a 342 eV and so on. So now when I am going to draw the same, how the energy levels are quantized, that is, this is E0, this is E1, E2, E3, E4 and so on. Okay. So in E1, so how much amount of energy is released? So in E1 the amount of energy is released is 34 eV, and in E2 the amount of energy is released is 152 eV, and in E3 it is 342 and so on. So it means the energy of an electron in a potential well is quantized, but not it is continuous. That is, discrete energy level exists for the electron, and the same the wave function is given by, this is psi 1 square, this is psi 2 square, and this is psi 3 square and psi 4 square, and the energy is E1, E2, E3 and E4. This shows that the discrete energy level exists for the electron, and as well the wave function in these discrete energy levels are given by psi 1 square, psi 2 square, psi 3 square and psi 4 square. So this is what the conclusion, so given by the Schrodinger's wave equation. Therefore, the energy of an electron in a one dimensional potential box is given by the expression E is equals to n square h square by 8 ml square. So where L is the width of the potential bell, and for example if I am going to consider L as 1 angstrom, so and where n can take values 0, 1, 2, 3, so after substituting these two values it comes out to be, for n is equals to 0, so that energy is 0. That is, it is a 0 point energy. So that is, energy is not yet started. So for n is equals to 1, in substituting this expression, it comes out to be E1 is equals to, so n is equals to 1 h square by 8 ml square, and substituting the values of h, m and l for 1 angstrom width of the potential well, if I am going to consider, it comes out to be where h is the 6.624 into 10 power minus 34 and m is the 9.1 into 10 power minus 31, and for 1 angstrom, so it comes out to be 34 eV, and for n is equals to 2, it comes out to be, so 4 E1, so it comes out to be 152 EV, and for n is equals to 3, it comes out to be 342 EV and so on. And let us draw the eigenvalues and this Now let us draw the eigenvalues and wave function of the above expression. So it comes out to be for, that is, the energy of an electron in a one dimensional potential box is quantized. That is, discrete energy level exists for the electron. That is, there are different energy level exist and electrons are supposed to move only in these discrete energy levels. That is, the E1 energy level, E2, E3 and so on. Likewise, the different energy level exist for the electrons. And in the first energy level, so how much energy is electron is released? Energy is going to be released by an electron in the first energy level is 34 eV, and in the second energy level it is going to be released as 152 eV, and in the third energy level it is 342 eV and so on. And the same, the corresponding wave functions of an electron in a one dimensional potential box are given by, so this, the length of this one is x is equals to 0 to x is equals to L. So the wave function in the first energy level, so this is the motion of an electron, and in the second energy level this is what the motion, and in the third energy level, so this is what the motion of an electron. So this shows that, what are the conclusions of the Schrodinger's one dimensional potential box? The one dimensional potential box conclusions are, that is, the energy of an electron is quantized. That is, there are discrete energy level exist for the electron in a one dimensional potential box. That is, electrons are not free to move throughout the volume of the crystal, but the thing is, the electrons are supposed to move only in a discrete energy levels but not randomly. There are discrete energy levels are discrete energy levels are there for the electrons, and this is, we call it as the energy of an electron is quantized. And the one more important one is, so as we know that E is equals to n square h square by 8 ml square. So this shows that E is inversely proportional to m. E is inversely proportional to m here. That is, the energy of an electron is inversely proportional to m, and as well as it is also inversely proportional to the width of the potential well. That is, E is inversely proportional to m, and as well it is inversely proportional to 1 by L. So in both the cases this is energy is inversely proportional. So these are the conclusions from the Schrodinger's one dimensional potential box. Thank you.